Hello, ladies and gentlemen. I am Dr. Claudia Albers, Planet X researcher and professional physicist. And today I'd like to bring to you another one of my articles. This one is entitled Planet X Causing Earth to Move Away from the Sun. Now, the Sun has been drained of gravitational energy for over 150 years. And you may look at the article entitled A Planet X System Time of Arrival for more details on that. And it has been drained by the Planet X system of gravitational energy depleted or dead stars and planets, which are also called stellar cores. The name stellar core is appropriate because what is left of these objects is the solid dense core of the object and a small amount of material around that core. The rest of the material that was once a part of the living celestial object, star or planet, would have been lost long ago. This occurs because energy-depleted celestial objects lose their gravity. The gravity, or the ability an object has to attract its own matter and other objects, is dependent on their gravitational energy, which is generated through radioactive decay in the core of the object. You may look at Article 192 entitled Neutron Stars and Fission as a star's internal energy source for more details. Once there are no more nuclei to decay in the core, the object becomes energy depleted, which is analogous to its internal battery having run out of energy. Once the energy is depleted, gravity sharply declines. And you may look at Article 249 entitled The Photon Field, Gravity, Anti-Gravity, and Gravitational Energy for more details on that. In addition, gravitational energy depleted objects absorb energy from objects that are not energy depleted. And this is the reason why the Sun and all the planets in the solar system are being drained by the objects belonging to the Planet X system, which have invaded our solar system. And you may look at Article 244 entitled Planet X System, Destroyer of Star Systems for more details on that. And in this diagram, what is illustrated is how a photon moving through space at the velocity of light splits into particles which have mass, which have energy within them in the form of photon energy, also called gravitational energy. And if the photon has an energy of 940 MeV or above, what it does is it splits into an electron and a proton. This is because the particles were already inside the photon, but they had not manifested. They only manifest once the photon moves through a region of high enough electric field, at which time they are split apart by the fact that one is positively charged, the proton, and that a positively charged particle will move in the direction of the electric field, whilst a negatively charged particle, and the electrons, a negatively charged particle, will tend to move in the opposite direction. So that means that when the photon moves through an electric field, the electric field pulls the two particles apart and they emerge from within the photon, at which time the photon energy turns into the mass of the two particles, and what is left turns into gravitational energy or photon energy, which is then confined to being inside the particle. So it's like a turning over or a reverse of what we had before. We had particles within photons, and now we have photons within particles. But what also manifests is the gravitational field of the particles, which is dependent on the mass and on the energy of the photon within the particles. And in this way, it is a manifestation of a photon as well. So the gravitational field is a photon field. And there are two types of fields. There's the gravity field, which is like the well-known field that we know that it causes planets to be attracted to stars or moons to be attracted to planets. which causes objects to fall down towards the surface of the Earth within our planet. And that field is due to the gravitational field that protons have. So it's called gravity. Electrons have a field which is opposite to the proton field. It has an opposite direction to the field on the proton. So I've called it anti-gravity. It acts against and is repelled by the field of the proton. So we have gravity and anti-gravity. We have the two because these particles have opposing fields. Now, we do know that photons split into particles because there is such a thing as particle-antiparticle creation. When, for example, a gamma ray splits into an electron-positron pair. And this is in the case of a gamma ray that has a lower energy than the gamma ray that will split into a proton and an electron. Except for one thing, we do not actually have anti-mass. There is only mass. So a positron is simply a particle with the same mass as the electron, but with a positive charge instead of a negative charge. And the two particles quickly recombine into a gamma ray because the strength of the gravity and anti-gravity interaction is the same because the two particles have the same mass. And this is explained in Article 182 entitled Einstein's Dream Realized Unified Field Theory of Electrogravitation. So the accepted gravitational force, the force between planets and the Sun, is due to the gravitational field generated by protons. The gravitational field generated by electrons has opposite polarity and is therefore called anti-gravity. Now, as the object being drained loses gravitational energy and the gravitational interaction strength G, called the gravitational constant in Newton's gravitational law, but which is not a constant, drops, and you may look at Article 210 entitled Stellar Core Gravity, tidal, and G is not constant. In fact, the gravitational constant is constant for one particular celestial object. It's the same throughout a planet or a star, but is not universally constant across the universe because it differs from celestial object to celestial object. And the evidence that stellar cores interact through a much weaker gravitational constant comes from the 2007 stellar core, which traversed the Sun in February of 2007. And we can see that particular stellar core here traversing the Sun. We can see it entering the Sun's corona, and the way we know that it was in the Sun's corona is because it was further away than the Sun's corona. It would look completely black against the background of the Sun, but in fact it looks red because there is corona between the object or the backside of the object and the detector. And we can even see it entering the corona because we can see that the part of the object that is not yet inside the corona looks black here. You can see part of that against the background of the corona, which goes further out at the edge of the Sun. And we can see it exiting as well, how it becomes black as part of the as that part of the object exits the corona. That part looks black against the background of the corona behind it. So this object was 2.2 times the size of Jupiter, because we could do a size comparison with the Sun. It was so close to the Sun. And you may look at Article 143 entitled Planet X Traverses the Sun, Irrefutable Evidence, for more details on this. And this object took 10 hours to traverse the sun, so it was traveling at 39 kilometers per second or 24 miles per second, which was a much lower speed than the sun's escape velocity of 616 kilometers per second. You may look at Article 153 entitled Planet X, Escape Velocity and Gravity. So the only way this object could possibly have escaped the sun's gravity, since it was traveling at such a low speed compared with the sun's escape velocity. And escape velocity just refers to the velocity that an object has to have in order to escape another object's gravitational field. So this means that this object had to be interacting with the sun through a gravitational interaction that was much weaker than is normal for solar system objects. And in fact, it was only 0.6% of the usual gravitational interaction strength that occurs between solar system objects. Now, this causes the celestial object to expand in size. So when the strength of the gravitational interaction of an object, or the gravitational constant for that particular object, decreases, then the object is no longer able to hold on to its own matter as strongly as before. So that means that it would expand in size, and for any satellite that it has would also move further away from it. So the fact that the sun has been drained of gravitational energy would mean that all the planets in the solar system would move away from the sun. And since the sun shows signs of being weakened at this time, as it is losing the corona and is much darker than it was a few years back at most wavelengths detected by the SDO satellite. And you may look at Article 195 entitled Stellar Cores in the Dying Sun for more details of that. It's very likely that most of the planets have moved further away from the sun. And here I just showed the 3 or 4 angstrom wavelength images over a few years. And as you can see, this was in 2011, 2012, 2013, 2014, 2015, 2016, 2017, and 2018. You can see how much darker the sun has become over the years, how the intensity of the light has so greatly declined, showing that the sun has weakened sharply over the years. And it did so independent of the solar cycle. We had solar maximum in 2014, but you can see that the sun, even in that year, was darker than it was in previous years. So the sun has drastically weakened over the years. And this is just one small part of the evidence. There is much more evidence detailed in Article 195 and other articles which I have written about the weakened sun. Now, the stellar cores have therefore a very weak gravitational field because they have a very small amount of photon energy left in its particles, like its battery has run down. When its battery runs down, its gravitational field decreases in strength. And here, a decreased in strength gravitational field is illustrated as the size of that gravitational field. In other words, the gravitational field, and it's a gravity field which is due to protons, it does not extend much further out than the edge of the object, and that means it's very weak. So the object, in order to interact with another object, has to come very close to it, and when it does so, energy flows from that object towards the stellar core. And this is what's illustrated here. This would be the gravitational field of the sun. This would be the gravitational energy in the sun's particles. and it's illustrated by this yellow ellipse here. So this is an object that still has a lot of gravitational energy because this is quite large, whilst a stellar core has a very small amount of gravitational energy. And so energy would flow from the one with a lot of energy towards the stellar core, and this illustrates how stellar cores drain other objects like the sun or the earth. Now, in order to see that a planet would move away from the sun, we can resort to a few equations. We're going to use Kepler's second and third laws in regard to the motion of the planets in the solar system. And the first law basically states that a planet's angular momentum is constant, which translates into this equation. Actually, this is Kepler's second law. And basically, it means that angular momentum is conserved. And we can say that L, where L here is actually angular momentum per unit mass, is equal to the orbital radius, r squared, times the orbital speed of the planet. And then we can rewrite the equation in terms of V. So V is L over r squared. And then we can look at Kepler's third law, which we can write in the form Gm over r is equal to V squared. And that translates into L squared over r to the 4. Using equation 1, where V is L over r squared. So V squared is L over r squared, which gives us this. And then we can solve for r cubed then is equal to L squared over Gm. And G, of course, is the gravitational constant, and M is the mass of the sun. Now, the equation thus implies that r, or the orbital radius, for the planet would increase if G decreases, okay, because they are inversely related. So we're going to go use a specific example, say for example that the sun has lost 30% of its original gravitational energy, which would mean that we would most likely have that the new gravitational constant for the sun would be 0.7 G. In other words, 70% of it is left. And that means that if we use equation 2, we can have the ratio of the new orbital radius divided by the old orbital radius. And that would mean that we'd have L squared over G nu m divided by L squared over Gm, the old G. And then the L squared and the m cancel. We end up with G over G nu, which is 1 over 0.7, using that expression there. And then we can solve for the new orbital radius, which would be r over the cubic root of 0.7. And that means that it would be 1.13, which means that the new orbital radius would be 13% greater than normal. And this would mean that the Earth would be 13% further from the sun than is normal. But a planet's orbital period, or the time it would take to complete an orbit, would also increase. So the length of the year would increase, which would cause the seasons, for example, spring, to arrive later. We can see this effect from another form of Kepler's third law. And Kepler's third law, and this is the usual form, is the period squared is 4 pi squared over Gm times the orbital radius cubed. Now, r cubed, we can substitute from equation 2, where r cubed is L squared over Gm. So if we substitute for r cubed, we get 4 pi squared over Gm times L squared over Gm. And then we get 4 pi squared, L squared, G squared, M squared. And we have T squared on that side. So we can take the square root on both sides and get T equals 2 pi L over Gm. Then if we again use the fact that the new gravitational constant is 0.7 of the old one, and we substitute we use the ratio, so T nu over T is 2 pi L over G nu times N divided by 2 pi L over Gm. Then the 2 pi L cancels and the M cancel. We just end up with G over G nu, and that would be 1 over 0.7, so we would end up with 1.4. In other words, the new T would be 1.4 times the old T. And this would mean that the year would be 40% longer, as the orbital period would be 40% longer than normal. So the fact that the sun is losing gravitational energy to the stellar cores indicates that the sun's gravity will be affected, and that this will result in a reduced strength of the gravitational interaction, which is given by G, the gravitational constant, in which case the Earth is now further away from the sun than before, which would cause the sun to look smaller in the sky from Earth. But this would be masked by the global sun simulation system, which hides the presence of the stellar cores and the fact that the sun periodically goes completely dark. And you may look at article 226b entitled Sun Simulating Devices, the Irrefutable Evidence, for more details on that. In addition, the length of the year would be affected and the seasons would not come at the correct time. The Earth is not likely to cool down as a result of moving further away from the sun, though, as the Earth is also being drained, which would cause a greater amount of heat to flow outwards from the core. This is because when Earth's gravity decreases as a result of the energy drain, or G decreases for the Earth, the radioactive decay rate is likely to increase, resulting in more energy or heat being released from the Earth's core and flowing outwards through Earth's many layers toward the surface and through the atmosphere. And you may look at article 240 entitled Planet X System, Effect on Radioactive Decay Rate and Heating of Planets for more details. And this is illustrated in this figure, how a stellar core absorbing energy from the Earth will cause the Earth's core to just decay, cause the nuclei to decay faster, and so more energy flows outwards through the layers, causing all the layers in the Earth to warm up and reach higher temperatures, therefore. So in conclusion, the fact that the Earth is losing energy to the stellar cores is likely to increase both the orbital radius and the orbital period of the planets in orbit around the sun. This will make the sun look smaller in the sky from Earth and the seasons to be delayed, because the Earth's orbit around the sun will take longer to complete. And here are the references. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.